Newton, right? He's in the back of a $100 bill. Yeah, I don't know. Newton, the guy who stood under a tree and an apple fell on him, right? And then somebody shot it off with an arrow. That was William Tell, was it? Anyway, Newton, the guy associated with gravity. And he came up with some rather interesting relationships, relationships, equations that predict the rate of motion of bodies. I was going to say heavenly bodies, but I'll refrain. Heavenly bodies too. No stars out there. In fact, the space launches and so on would not be possible if Newton hadn't stood under that tree. So, I mentioned acceleration associated with that focal plane shutter. Well, acceleration takes place whenever you drop something. Beginning it moves slowly, and then it moves more quickly. And it keeps going faster and faster and faster. The farther it goes from the place where you dropped it, the faster it moves. Now Newton was smart enough to figure out how fast those things move at a given distance from drop. Did you ever do this experiment in physics class? Well, this is a chance to correct the situation. So, I had this concern that maybe Newton didn't get it right, and I'd like to prove it. Either prove Newton right or wrong. So, what I'd like to do is to see how close Newton was in the original prediction that he made as to how objects in motion accelerate due to gravity. There is a particular relationship. I think you're going to get this in a piece of paper. That says something to the effect that goes like, I better not improvise. Although this is the hard way of saying it. The velocity of whatever object squared is equal to 2 times acceleration due to gravity times s. This is and this is distance from rest. Okay, now there are a bunch of other equations that precede this, but eventually you get to this one. And this is the one that I would like to prove right or wrong. Now, another way to write this, because velocity squared is kind of weird, I'll do this instead. I want velocity. I don't want velocity squared. But if it was squaring over here, what do I do on that side? Yeah, square root it. So given this, I should be able to draw a graph of what Newton means by this equation. The graph will be set up like this. This is the output, which is velocity. And this is the input, which is distance. Right? So over here I'll have foot, 2, 4, 5, 6, 7, or inches, whatever you want. And over here I'll have velocity. This will be in feet per second or kilometers per hour or whatever you want. Well, it can't, if this is in feet, then this has to be in feet per second. But if it's in meters, then you could do something with it. So this is feet per second, and that's distance from rest. So I could pick at random some distance, let's say 2 feet. I want to find out how fast, and this is in the absence of friction. Okay, this would be in a vacuum. But we're gonna get, we say, you know, we're close enough to vacuum. I can feel it. So we're at 2 feet, and we're gonna drop something, and we can now put things in here, right? The number for acceleration is 32 feet per, and of course this was worked out on another equation. Feet per second per second. The distance from rest is 2 feet, right? So what I'm looking for at 2 feet, the velocity, which is, what, 2 times 32 is 64, times 2, which is 128. I'm looking for the square root of 128.
Anybody?
Should be something like 11. What is it? You got it?
It's all online.
Yeah, I'm blind. The problem is my eyesight is not very good. But if it's 11, 11 times 11, right? Lines up like this, 11, 11, 1, 2, 1, correct? Well, I'm trying to do this multiplication in my head to show you that we can do that. You don't need a calculator. So we're looking for a number anyway that when multiplied by itself equals 128. And 11 something or another is close. So that means that wherever this says, if this is 5, 10, 15, 20, 25, 30, where it says 11 something, we put a dot at the 2 foot distance. Okay, well, let's figure out what it is at 6 feet. 2, 3, 4, 5, 6. 6 feet. Well, what do? Well, all we do is change this from 2 to a 6, right? This stays constant. It stays 2 times 32, so it's 64 every time. 64 times 6. Well, let's see. 6 times 4 is 24. 2, 36, 38. 384. Yeah, but we want the square root of it. The number which will multiply by itself is 384. Well, how about 20? It's not right. But 20 times 20 is what? 400, right? That's pretty close to that. So it's going to be 19. So at 6 feet, now we go to 20, and we'll put a dot there. Or wherever it would be, the square root of 384. And then if you do the in-betweens, you'll end up with some kind of a graph that might look like this. So that you have all in-between points. So you say, well, oh yeah, this is what Newton says. Now let's prove him right or wrong. How do we do that? Well, we have to find out the speed at which things are moving at given distances from someplace where we got it. I erased the one that I didn't want to. So I'll erase everything. So, how are we going to find out now this is the first time that this will ever be done in this course. So how come I have one of these ready to pull out of it? Anyway, so here we have a scale, a ruler, or something that has markings on it in each part and other markers on there that are a foot apart. Okay. So we say, okay, suppose we aim the camera so that we see this mark here, so that that is in the middle of our frame. Middle frame. And the neat thing here is, again, the camera on its side, because the shutter is going to travel along the long dimension. And we have in here a ruler, and it has a marker on it. It says this is 0. Above it, there are some inches, and then there's one.